Okay, thank you very much being here. My name is Jonas Lindemann. I'm from Lund University. And this will be a bit less codey talk, I think, than before. This will be a bit of a time travel back in time to around 2000 and then going forward to present day with a single source code application I've developed called ObjectiveFrame. So a little bit about myself. So I actually started in instructional mechanics. I have a PhD in instructional mechanics, where I actually got to do a lot of development work, developing user interfaces for finite element applications for architecture and designers. So not so much engineering, but designers. I did a component-based finite element model, both in Corva, but also in component object model. I developed a lot of visualization techniques for fiber networks, and I code mostly in Python, C++, and Fortran. I'm also the director of Lunark, which is the high-performance computing center at Lund University. Some of my applications I've developed, you can find some of them in the App Store, and some of them you can download. All of them are open source. So ForcePad is a 2D finite element application. ObjectiveFrame, what I'm talking to now. I have also developed application for simulating hardening concrete called Hakon, which is in Pascal, and some other tools here. In my spare times, I do a lot of creative coding in processing, Pi5, and renoise. I also have written some books. So I have a Swedish book, The Engineer's Guide to Python. I have an online book in Fortran. And also I'm working on a scientific program in C++, which will come online soon, I think. So I teach a lot, and in different languages as well. So how did we get to ObjectiveFrame? So this happens when I worked as a PhD student in structural mechanics. So I was really lucky to get a position with a very open kind of track. It was not said that I'm going to do explicitly something, but I could work basically in every area to kind of develop new user interfaces, which was not the computation model, but user interfaces for the computational models. So develop new interactive tools. Primarily they were used in early design work, so for the architecture and designers in an early phase to get a feel of the structures and the forces acting on the structures. So conceptual design, and also in teaching and learning, because that is something we saw at the university, that understanding mechanics is important, and it's hard to do that with just calculating on pen and paper. Visualization as well was part of this, of course, because you need to visualize the forces. So this was my dream come true. So I got kind of 5 years doing programming in C++ and other languages, and doing visualization and graphics programming. So that starts kind of process getting to ObjectiveFrame. So virtual mechanics workbench, that's kind of theme of this application. So imagine a mechano box with parts that you can put together yourself and experiment with. And in mechanics, that could be, for example, you see in many airports, you have these frame structures in the roof connected with balls and joints like this. And you can see here in a larger one of this, where you can put together beams with nodes, connect them together to a structure. And as I actually found pretty recently, there is a company doing this completely mechanical as well. You can buy these things and put together and do the same thing mechanically. So ObjectiveFrame does that, but as a software in your computer. There are 4 major components that you work with as a user. It's the node, where you connect your beams to, and then you add your loads and forces onto these elements. And then you can attach everything here in using boundary conditions here to make it not float away in space. So the goals were develop a tool for understanding forces and structures, reduce user interface complexity, because that was something that was problematic with the existing engineering tools, that they are very generic to kind of solve every problem an engineer could have. Also try to use direct manipulation and feedback. So if you push a load on something should happen directly. So kind of develop a model shop for architecture and design where they can experiment easily and quickly with quite complex structures. And also try out their own designs in an easy way. So one thing I started at that time, so this is early 2000, gaming kind of started coming to PC with hardware acceleration. So I think, could we learn something from games? So most games have, of course, direct interfaces, direct interaction with the world. Often you kind of don't start with the Windows user interface guidelines. You kind of start creating new paradigms for interaction with models and objects. They should also be visually appealing, so it's fun to use them. And they should be also easy to learn. And also, there is always an animation and real-time interaction factor of this. So just kind of give you a flashback at the era where we started ObjectiveFrame. You probably know this. This is Half-Life. There's Free Space. These kind of early hardware-accelerated games when I started developing. So I got inspired using transparency, dynamic lighting, direct manipulation, heads-up display, all that stuff. So that kind of inspired me to, can we do something similar in mechanics? So just give you a flashback here. Once upon a time, so what was it like to kind of develop applications in this period of time? We started to see new hardware possibilities. So cheap hardware, cheap 2D, 3D acceleration. You can have real-time lighted and shaded models, transparency, fast 2D operations. The computational resource also started to increase, that you can have, the PC started to get more powerful at the time as well. So you can do a lot of computational things on a PC. And also, you can also do on more complex, on bigger workstations, you can do more complex analysis as well. And sometimes even in real time at the time. So the problem was, so platforms of 3D development in early 2000. Not many, and there are some really expensive, and they're not always so mature either. So just kind of give a view here what we're working on. So these were the platforms when I started working in my PhD. You had the Windows environment, the PC, and we have a Unix environment, workstation environment here. So I had Windows NT, also Windows 95, early OpenGL hardware. I also had a SGI workstation with really cool OpenGL hardware. So that made it really fun to kind of start 3D coding. So just kind of give you an start. This is what I got on beside my desk. A really cool machine. And you can do all that really cool stuff that you couldn't kind of dream on a PC. Starting to get there on a PC, but this was kind of even more cool. And you can program this in C++, of course. And yeah, that was kind of how it started. But I also had this, the kind of classic beige box to kind of develop for Windows. And starting to get there, OpenGL cars that could actually do OpenGL, window-based and so on. So that's kind of the base for what its ObjectiveFrame started. So how do you create a platform-independent 3D application? So I had a SGI workstation, I had a Windows machine, and I would like the application to be able to run on both, to do cool stuff on the big workstation, and also be able to make users be able to use a PC to run the same application. So we had OpenGL on both platforms, both Irix and Windows. So for Irix is the operating system for Silicon Graphics workstations. And you can already ID software showed that you can run Quake with OpenGL on a Windows machine, so that kind of showed that it is possible. And there was reasonable support in OpenGL on Windows at the time as well. But it's kind of hard to get the hardware, but you could find it. So I found some of the cars to do it. Another problem was kind of C++ compiler was available on both platforms. And we are talking like C++ 98-ish compilers. So, and also we had the Visual C++ 6.0. And on the SGI machine, we have the MIPS Pro compilers. and they were not very compatible. So Microsoft had their own quirks in their compiler. MIFSPER had really a lot of them, and also were kind of behind on the standard side. So it was not super easy to get them to work, but I could at least compile my code on both platforms with some defines and stuff like that. So the first part we needed for the application was a user interface. So user interface libraries at the time, the situation was quite different than it's today. There was a lot of copyright issues, platform lock-in, and not much interoperability. So if you look here, so this is the Linux desktop based on Qt and KDE. On Windows, we had MFC, also Qt, but I come back to that later. And on the Silicon Graphics, we have OSF Motif X-based user interface. So you really don't want to write one application for every platform. So you want to do something platform independent. So platform independent. So MFC locked to Windows. I couldn't use that if I want to use the SGI machine. OSF Motif, too complicated, and I can't run that on Windows. Qt required a commercial license on Windows at the time, so it was not open source at the time. So of course I could compile it on a Linux machine and work with that, but not so ideal. So I got a tip from a friend that works kind of in both worlds, and he said there is a user interface library called FLTK. It exists today as well. And it actually compiled out of the box on both platforms. It had other features as well. So it supported OpenGL on both platforms without any additions. So it opened a window where you can code OpenGL directly on both Irix and Windows. And it had a user interface designer as well. Oh, yes, that's cool. So I chose to use FLTK as the base layer of the application. So just shortly about FLTK. So yeah, it works on Windows and Irix and has OpenGL built in. So it's basically just open a window, say I want to do OpenGL, and you can run your commands directly. It creates the context for you automatically. Fluid user interface editor. So a graphical editor that generates FL files where you can import them into the code, and you can generate C++ code from those FL files that you can then compile into your application. And it's two ways. So you can, if you don't edit your generated files, you can go both ways. And it really works on platforms without magic, or at least there is perhaps some magic in the library, but it worked for me at least without any magic. And now I'm just warning you, you will get to see really old user interface examples here. So yeah, this is how it looks. This is the fluid user interface designer. And you see you define all your objects here. Those will generate as C++ source code. And this is a typical Windows XP fluid user interface generated in FLTK. You can see here the thing is that the window here with a checkered background, that is actually OpenGL. And there's no magic, you just open it and you can draw directly into that window. So next, now we have the 2D parts. So we also need to have some way of doing the 3D stuff. Yeah, you have OpenGL. I can do it in Windows NT and C++. I have the C++ tools available. I can compile. But what was it like at the time to program 3D graphics? So this book I found at home, which was by my kind of Bible at the time to kind of implement the OpenGL stuff. So it was 1.1 and 1.2. And this is kind of the things you found online. There was the GLUT examples that you can, Mark Kilgard did from SGI, and you learn from that. And for prototyping, the SGI version works perfectly. I mean, all the OpenGL things just work, and it has high performance. I had OpenGL on Windows, but it was really hard getting fully compliant hardware and also getting a code work exactly the same on the platforms. So OpenGL was, that 3D was an option, but of course I can't go to the Silicon Graphics machine with that. So I used Windows NT4 with a graphics card to work on Windows. So I didn't want to code everything. I really did want to have some kind of 3D library to work with. And at the time we had, options were limited again. So Open Inventor was a C++ library from Silicon Graphics. And you come back to this again, no version for Windows. OpenGL Performer, only for SGI machines, but really a bit too level, but also it was hard to get other platforms. OpenSceneGraph was not released yet. So yeah, that was the situation I had. But so what do you do now? But as many PhD students, you have unlimited time. So of course you implement your own SceneGraphs library on top of OpenGL. So it's a little bit like this, but instead of standards, we have SceneGraphs libraries. So, and all of a sudden we have 15 SceneGraphs libraries. So the result of it, I developed something called Interactive Visualization Framework, which I used in most of my research. Lightweight C++ SceneGraph library implemented on top of OpenGL. It didn't become so lightweight. I added a lot of stuff to it. But object-oriented, generally you could use SceneGraph, so you have this tree structure you can traverse. There was a basic user interface framework for bringing up windows easily. You can load images, load models, and I also provided several interface widgets for different toolkits, so for Win32, FLTK, MSC. I had a lot more time at the time, so it's. I also released it open source, which was a bit. My department, structural mechanics, they were kind of not used to that, so it was something also that you have to kind of explain that it could be useful to do it. So we did it, and I released it around 2000 or something like that. It was downloaded quite a lot at the time, and I got also some image loading routines from users that used the library. And you can find it on GitHub today, because it's actually the thing that I'm basing ObjectiveFrame as well on, so there are versions of it. So let's see here, I'm just going to zoom in here a bit on the directory. So base class. I have a class for implementing the GL functionality. And we also have a basic shape that is the basic node of the scene graph. There are state classes here for implementing the different fixed function states, material, textures, and also all the primitives of OpenGL are available here. So you can easily create chord sets, line strip set, and so on. So it contains basically all the things I required for implementing ObjectiveFrame as well. So GL base, that is for classes that will render and use OpenGL context. It has a state here, and you can also add you can turn it off and turn it on and so on. And then you have a shape that is the kind of major node that you can attach a texture, you can attach a material to it. It can have a position, and all the other objects that you can render on the screen are derived from shape. So just kind of how it can look. So this is the an IBF++ application from the time. So I tried to kind of modularize it and put the different libraries and different folders in the includes. I used a lot of at the time Microsoft notation, so I didn't have any namespaces, so I had namespaces in my names. This is the main application here, but I actually used smart pointers, so I started to use it already then. So you can see here, this is defines for smart pointers for the light and camera. And then you can create the camera, set position, set perspective, create a material, create a scene, have a cube here and add that to the scene, and so on. And it kind of encapsulated a lot of the OpenGL functionality which were required in my code. And this is the main application here. So I also provided some classes for creating application, creating a window, and also rendering application. So you can use the library without GLUT, or knowing how to use a GLUT application, so you can code directly in this one here. So next step in my implementation of ObjectiveFrame was to kind of create an object-oriented model of a finite element structure. So you're a PhD student, you want to think very general, so I did a lot of object orientation. I created a lot of classes, and I not always did a perfect design choices. But so the idea was to design something that could support interactive use. And I also have some ideas that I wanted the computation model to be separate from the visual model. So I had two object classes, libraries, one for doing the computation and one for doing the visualization. So I have OFEM and VFEM. And so afterwards, I'm not sure that this was the completely right choice, because now I had, so the visual classes refer to the object model, and you have to kind of go between them to update them. And it kind of worked, but a bit too complicated when I now look back at it. So that is also something I'm trying to learn, to make object orientation a bit, simplify my class structures. So this is the object tree here. So this is a lot of mechanics here. So I have material, beam material, I have load set, loads, elements, which is the basic building block of a finite element application. Then I have a beam, which is the basic building block of this application. I have beam sets, node set, load sets, there is a lot of them. The main functionality is the beam model. And the beam model contains all the instances of all the nodes, all the elements, all the boundary conditions in a single class. So let's see here. You can see here I have the element is the basic element that has nodes connected to it, and there also the basic computational model is in the element. So this is an abstract class. And then I have a beam here that overrides some of these and specializes the element. And this is an element set that is also one building block that contains the elements, and you can work on them together. And then there's a beam set, of course. So I was very happy doing object orientation at the time, writing a lot of code. So I will just, and here is the thing that I was a bit, I don't like really anymore now, is on the left side here, you have the visual implementation of the beam that can draw itself. I have a node, which is a visual representation of a node. And then you have pointers that points to the actual node in the computational model. And that has to kind of, and there was no, so you need to kind of keep both models in sync, which I managed to do, but when I look at the code now, it's really complicated. So I just skip that. So computational engine. So when I have the object-oriented model now, I need to be able to solve the system of equations. And at the department, most of us worked with MATLAB at the time, and I needed to find a way to create going from the MATLAB algorithms to a C++ model. And at the time, I'm not sure if you know about the Newman library, but I found it online. And this is a matrix library written by a guy in New Zealand. So, and the thing with this C++ library is actually, you can almost translate the MATLAB code directly, because it contains all the necessary things to implement that you have in MATLAB that's in C++. So I found this here, and Robert Davis in New Zealand is I think he's over 80 now, and he still maintains his web page with this. So it's impressive. yeah, easy to compile and worked with Windows and Irix, so there was a thought of that as well. Very similar to MATLAB. Several easy to use solvers as well built in. And this is an example of code here. So you can very easily create column vectors, row vectors, matrices, and initialize them using familiar C++ syntax. You can do element-wise operations, and you can do matrix operations. And you can do matrix expression as well, just like you do in MATLAB, basically. So it's very similar. And that made the job very easy to implement the solver in my code. This is you can easily create a linear equation solver here, and you can just solve the system like this. So what have we now? So let's put the pieces together in the final application. So at the time, we had Windows and Irix at the bottom here. Top of that, we had Win32 and X11 as the user interface libraries, OpenGL. And on top of OpenGL, we had IVF++, user interface library FLTK, and the NewMat library for solving the computational model. And then I had the OFEM library, so that is an internal module in the application. So that is the computational description of the model. The visual computational model, VisFem. And then the util library is not that big, but it became big. And then ObjectiveFrame on top of that. So the first version looks something like this. You can see where I found my exploration at the time. So it's kind of like Half-Life-y. Transparency for the icons, of course. Also heads-up display for the hint boxes. And I will show you how a video here about how it works. At the time, I couldn't just kind of get the feeling of the interaction at the time. So I will demo this live as well with a new version as well, but just get the feeling. So these were the kind of models we could do in real time, basically. And I then it displays the forces in the beams as well. So in my research, we tried it out on some unexpected architecture students. So they had a course in large structure buildings. So the idea was that they got two pre-built models, and then they had to reinforce those models in different ways to study the different effects. And it worked quite well when you gave them complete models. But there were things that worked and some things that didn't. So it worked as a proof of concept, as a real-time mechanics application. And we could use it in teaching with pre-made examples. And also, the platform that we developed worked. What did not work? It was too complex still for new users to learn. So that is something we learned quickly. And also, I was way out designing dialog boxes to make the application really general and really, it became an engineering application, which is kind of not what we wanted. And it was really unstable. Yeah. And also, no undo, which is also really frustrating for a lot of users. I don't know why, but. So we did some user testing. So we got a lot of feedback here that to kind of get better feedback where the application, which state the application is in, and also better ways of creating nodes, because 2D, having a 2D interface to a 3D world is hard, and also if you want to be precise in placing nodes, so we needed something to improve there as well. View handling, we had 3 buttons below to change different views. There were no shortcuts, so it was hard to kind of move around in the 3D world. Better axis indicator to kind of distinguishes from actual other beams. So actually people were pressing on the axis indicator thinking it was a beam. Also confirmation dialogues for critical operations, mapping of rotation. So if you want to place a load, it's a vector. It's really complicated to kind of get a easy to use interface there to place a vector. So problems with stability. Yeah, it was new code. Basically, I mean, the course we tested it in, I basically had just finished getting something to work. And also, it's very hard to debug and test user interaction in 3D. It's when you see people using your application, it's oh, okay, you do it like that. So you have to think about it in different ways. Also, IVF++ used smart pointers, but the finite element code did not, which also was a problem and caused a lot of crashes. The complex class hierarchy, which separated the computational model from visualization model, was also too complex for its own good. And visualization class needed to maintain references between these classes, and which led to problems. So a bit intermission here. So as you know, when you are PhD students, you start with one thing and then you go on to something else. So I had to do other things. So I continued working on IVF++, but the ObjectiveFrame application was kind of put in the box. And I said, I will take it up at some point, but you never do. It just stays there. It was left unmaintained until 2013. Then I have a master student that was experiment with a leap motion controller. And I don't know if you know, it's a controller you can put on your computer which can track your hand. So it was pre-VR, but you can kind of manipulate the model. And that was one of the ideas of this application. So we did a major upgrade in 2013, making it compile again and making it work on Mac OS. So I used CMake here to kind of make a build system that worked on all platforms. Worked well. Added smart pointers to the FEM library, implementation similar to the one in the game engine design here. At the time, I didn't do any of the, I'm not sure where the smart pointers in C++ were at the time, but I used a lot of references from game development books to implement the smart pointers. And stability improved a lot. I had actually a lot of, so the scene graph actually had reference counting built in, but it was not connected to any smart pointers. So when I did this, I added this automatic reference counting. When you added something to node, it added the reference count to the actual node as well. Also, I got to give it a slight new look and feel. View handling with shortcuts as well. I changed a lot of things in that code. So I have this FEM smart pointer here, which is a define that defines the smart pointer for the CFEM object. And I also added stud strings everywhere. And then I had, this is the smart pointer I have. So I had this FEM stud pointer from smart pointer to make it easier for myself to add the necessary stuff that I required for the smart pointers for the objects. And then I could start removing stuff like this, which is, So I had a lot of new delete things here with wheeled raw pointers. All that was removed. Also a lot of extra code that was not needed anymore because I have smart pointers. So, And then I gave this to my student, and he could start implementing the leap motion interface to the application. And you can see here, he based it on some of my code as well. And then you can see here we got a cool application here where you can actually pull the nodes, and it will deform as you move the hand over the code, over the structure. I did a minor upgrade in 2018 again. And I started to kind of realize that this was not working anymore. So the application didn't provide any anti-alias rendering because FLTK couldn't support anti-alias rendering on Windows, which was really annoying. So I thought now we are kind of at a dead end of the current implementation. So I thought we need to kind of really do some refactoring of the code. So a more modern Frame. So what I was thinking about was doing immediate mode rendering to kind of make the user interface even more responsive. So FLTK is a stateful user interface library. So let's kind of leave that and see if we can do completely immediate mode rendering. Reorganize the code as well to make it more structured and easier to work with. Try to add a new matrix library. So I had some goals for this. So a new user interface framework that worked better with OpenGL, more modern look and feel, immediate mode user interface, better matrix framework because NewMat is single threaded. And it works to some certain degree very well, but then it kind of, you can't scale it more. So I wanted to have something that could do multi-threading, had a more modern C++ interface, and interface with the math libraries. Undo. Move IVF++ to modern OpenGL. Embed a scripting language because that is something, there's a lot of structures you want to create that are complicated. And it's really hard doing manual, putting a node and drawing a line. So you want to be able to create scripts that can do, to create this geometry for you. And I was also considering having an external scripting interface so that you can use it from our Python tools that we also provide to our students. So those were some of the goals. I did some general code modernization, namespace for all libraries, remove all the strange class prefixes I had. I actually used some of the tools that are built into Visual Studio Code to do some of these stuffs. Replacing new everywhere. I found new everywhere I looked in my code. So I know that Klaus said something else, but I call it factory method. But I have added create methods to all my classes that creates returns a smart pointer. So you can do stuff like this here, auto beam create. Also, I had I'm not sure what the password at the times. I had thousands of defines instead of enums. So I also changed that. And I listened to Jason as well to kind of fix all my compiler warnings. Some of them I still haven't been able to fix because they're interaction with the libraries, but they are not mine. So I skipped those. Added const where possible, replaced some of the C string interfaces I had with std string, used Clang format for consistent formatting everything on my source code, used Clang tidy and Visual Studio tools to actually do some static analysis of the code as well, which also found some interesting things. Try to use range-based loops where possible, and also use order to simplify code, for example, when I use iterators and template types. Some of the things I did here is going from that kind of defines to enum classes instead. So instead of having B as no error here, you had model state equals model state OK and so on. It looks nicer. I also did use the std function things in C++ to implement a more modern logging system here where you can assign functions for logging that could reach all the libraries I have in my code. Let's get that. So this is the logging window here. Another thing I did was path handling. I also found a lot of paths manually added string manipulation to create system paths. And that is really, if you work with 2 platforms, now 3, it's really an issue. So you can compile it on one platform, run it on a Linux machine, it just crash. Okay, I fix it on Linux, run it on Windows again, it crashes again because Windows has backslashes. So what I found, I used std file system here to actually use that consistently to create paths instead of relying on my own kind of coding skills. So I had stuff like this on the top here, rfind / substring, all that stuff, and then instead having std file system and then adding it together here in a consistent way without any even giving any backslashes or forward slashes. So now we have this situation here. We have 3 user interface libraries to work with OpenGL, IVF++. We need something here. We need something here. We have OFEM, VisFem, util, and then. So we need to find those 2 missing boxes here. So I started looking at IVF++ because it's old and I needed to modernize it. And I realized this is a really large library, which I haven't worked on for several years. And also how much time do I have, what works. So my conclusion was that the basic principle of the object model works. It uses the OpenGL fixed function pipeline, which is deprecated, sort of. All graphics vendors today actually support it still, so it's there, but it's not modern. So also some of my selection methods to select objects in the scene was really not working well on different graphics cards. And I also extension interface. And what I did was I refactored all the namespaces, changed it, and I also added this create method on every class to be able to easily create smart pointer references. But after some tests, I decided to stay with the OpenGL compatibility profile. It was at the time too much work to refactor, and I'm preparing for a later upgrade. I have a version 2 of the library that is not compatible with this one at all, but it uses a more modern OpenGL. But for this application, it's really hard to change everything. So I decided to kind of step back. I replaced the buffer selection that is built into the fixed function pipeline with ray intersection algorithm, so just geometry, basically. And it actually works well. I used the GLAD tools to generate an independent loading of OpenGL, which is also something that is interesting. It's different on every platform. So I replaced the GLH with GLAD GLH instead. Yeah, method for creating smart pointers added. Actually, this is something that I have. I worked in Object Pascal several years ago, and all the objects in Object Pascal have this .create method, which I think is really nice to have instead of the long things you can do in C++. So I released this as 1.5, and it's available on GitHub as well. So now we have another box to solve on how to move from FLT code to something else. So I had some idea, immediate mode rendering. So my idea was to, can we move a complex application from a stateful application to something that can use a intermediate mode rendering interface. So if you have heard it, there is a nice library called ImGUI, and I think most of the game libraries today actually use this for console or backend access to the gaming engine. So this could be an interesting research question. Can I move my existing application to immediate mode interface? So this is Dear ImGUI. So it's a stateless UI toolkit. That means that you render the user interface every frame all the time. There is no objects. You just kind of call functions to generate the user interface. And it's created by Omar Kornat. It's very active on the internet. And it integrates basically into existing frameworks. So you can't take it on its own. You need to kind of connect it to something. And that something is DirectX, OpenGL, Metal, or Vulkan. So it can render in any of those. It runs on all platforms. The only thing it lacks is Windows. And not Windows operating. It needs Windows because it doesn't provide any way of creating windows. So and this is how you use it. You create a window, and then you have a loop here that you draw continuously. So here you have the commands here, OpenGL, new frame, begin. So this actually draws things on the screen, and this is done continuously 60 frames per second. So, yeah. I read also there's a lot of user interface classes implemented in FLTK now. So how do you move them out from this existing application to something else? And also replacing everything at once was not an option. I mean, it's quite a large code base I have here. So what I did actually, I created an FLTK interface widget class that could render ImGUI inside FLTK. So I started with application, the old application, added this kind of interface, and then started moving over the user interfaces one by one. But I still had, every compile I had a working application. So I moved one dialog at a time. And I used the ImGUI OpenGL application as a base. One problem is that FLTK doesn't have a continuous rendering loop. So I need to kind of fix that. And what I did was to added a timeout method in FLTK to actually force a continuous redraw of the OpenGL window all the time. It's a bit of a hack, but I'm kind of moving away from this library to something else, so I thought it was okay. So this is the ImGUI FLTK implementation. And here you can see I have a lot of code here that interfaces with the FLTK backend, but provides me with the same methods that I have in ImGUI to kind of start implementing stuff. So this is the widget, the FLTK widget, based on the FLGL window, and there's a redraw callback here that I add. So I force my own view to redraw all the time here. So of course, I like to do object-oriented modeling, so I created a small framework for ImGUI, because you have to write a lot of code to do ImGUI. So I actually try to kind of encapsulate and abstract some common boilerplate code. So I added OFUA to my base classes, which handles windows and pop-ups. And I try to kind of have similar interface what FLTK provides for this. So this is so I can do, for example, I create a node loads window. I provide my view to this, and then I can render this. So this has the window has draw, which is the calls all the ImGUI immediate mode drawing functions. You can have flags here to set it visible, show, hide, and so on. Make it more manageable. And then it can look something like this. So I still need to do the menu here in ImGUI. So you can see here you do call functions here, and then you have if statements here to depend what you're drawing. And then I have on the right side here, I have the model pop-up, and then you have a window list here. Here are all my windows here that also have this ImGUI code built in. And then finally I call ImGUI render. So what all this function does is creates a display list or some kind of list of things to draw, and then you draw that with ImGUI. So this is called every frame. And also we need some windows here as well. So to be able to draw. And there is no FLTK or no windows. So we need to find something else here. So what we did was that we need something to create a window and also an OpenGL context and an event loop. And ImGUI supports several platforms, so GLFB, GLUT, SDL, and Win32. And so what I selected here is I just go through here. So FreeGlut is a replacement for the GLUT library, uses the old API, and not many new features implemented. GLFB, so that is a modern toolkit for creating windows in OpenGL, and it has support for all modern features you have. You can handle multiple monitors, you can run on all platforms. Qt is also an option, but then we are back to stateful user interfaces again. So that I think I left that. So I chose GLFB as the base. And of course I did some objects here as well. So I have an application that runs the GLFB event loop. I have a singleton that tracks the windows. So I know if I create the multiple windows, I can get to them. And I have the main FemView window that kind of contains all the user interface. It's based on the GLF window class that I have developed. So this is how it can look. So I create an application, and then I set some hints for the GLFV, and then I create my window, and then I finally do app loop here as well. Yeah, I did some nice animations here. New computational engine. So we need to find something that can replace the excellent NumMat library. And as I said before, we need something that can take advantage of threading and modern libraries. Must be higher level as NumMat. And the three I found was Armadillo, which is also a very nice library, Eigen, and Blitz. And the one that I found was kind of closest to my needs was the Eigen library. It has very similar syntax to the NumMat library as well. And here are some, they are very superlative in their website, but I think it's true, it's very, very good. And it's a header only as well, and then you link with the libraries that you need, for example, the Intel Math kernel libraries or the AMD libraries. And the code looks something like this. The only thing you have to be, it's based, so NumMat have 1-based indexing. Eigen has 0-based, which leads to a lot of code problems because you have, everywhere you have 1 indexing, you have to think about it. So the solver is still available, so I kept the NumMat solver here, and I created a solver interface to be able to switch the different solvers. And there's a significant performance increase here. NumMat only supported banded matrices. Eigen has sparse solvers, which enables larger models as well. As I said, indexing errors. And also Eigen, it's very hard, it's actually really good to, if you do something wrong, it tells you. It has asserts everywhere. So if you try to do something and say, okay, you can't do like this, you're doing the wrong way. And it's really impressively implemented. The next thing I wanted to have in the code is scripting. So to be able to build models of geometry from simple scripts. And what I found is, Jason is here, using his library here. So I want something to create geometry and topology, because that is not, you don't want to do manually. And you kind of also need to add some functionality without large knowledge of compiling and linking C++. I also need something that can create a dialog box with some parameters from the plugin code. And then ObjectiveFrame will parse that script and create a dialog from that. So I tried first Python, but I found it was too complicated to integrate and too big for my needs. And then I saw a video from Jason about his ShyScript library, and it was really very easy to implement. A couple of lines of code. I created a script plugin module here that reads the scripts from a file, and that is my basic plugin here. And you can also add parameters to this. And then you load a plugin and run it here with the ShyScript interpreter. And you evaluate it here. And you also connect your code to the script library. So the functions I have in my finite element code, I add to this here, the necessary to be able to build models. So I have here add node, new model, and so on. And here's an example of a script. So the top part here defines the user interface. I have some special tags here that is parsed and interpreted and creates this user interface. And then it generates the geometry like this. I think I will skip the automation part here. I'm also providing external interface to talk to the application here, but I think I will skip to the end here. So what we have now is we have a base part here with Windows, Linux, and Mac. We have OpenGL, we have IVF++, we have ImGUI GLFV, so that replaces the FLTK stack. We have Eigen, OFEM, VisFem, OF solve, OF UA. So I divided up. I added a special library for the solvers, so I didn't interfere with the rest of the code. And I also have an OF service here for the backend interface to access it externally. So that is the web service. I will skip this. Yeah, I short thing about platform independence. It's hard to make it work on many platforms. So compiling around errors is the first step, but not the only step. It always almost works. And then you find some things like the file system problems, finding assets, paths, UI events not coming in the right order. I mean, that's, you design your application and you're looking, okay, the event for that comes in this first and then come next one, and then you run it somewhere else, it's different. OpenGL differences, so that I noticed, for example, for the selection behavior and for some other parts here. Common dialogues is also very different on different platforms. Yeah. So conclusions here. I think still, I'm impressed. I took up my code that was kind of almost 20 years old, and it was possible to compile it. And that is, I think that is impressive. And also for different OSs and different compilers. So you can still use old stuff. It's not always recommended, but you can. Refactoring can be hard. What I did is where I set up clear goals I wanted to do, so I didn't kind of start refactoring everywhere. I started certain parts and finished them. So I started with the IVF++. I continued with the OFUI, the finite element libraries. I also do it slow, incremental. So don't do too many steps at the same time, and also make sure that it builds between the steps. So small steps. Use smart pointers everywhere. That is kind of one thing I have learned in this project, to really do this, because it makes the application really much more stable. No new delete. Make it easy to use. So I do a lot of stuff like this. I'm not sure everybody does like it, but I think it's, for me, it's conceptually easier to understand. Setting Windows Putter. Use auto. Another thing that I noticed with this application is that when you do real-time rendering of your model all the time, 60 frames per second, you will hit bugs. If you have somewhere that you allocate something with a new or memory, it will leak. So also, if you do some interesting referencing of things, it will crash. So that was also a challenge here, that I found a lot of bugs that was not visible in my old application, but really came through when I did this. You can't have memory leaks in your model. And also, I found I had heap allocations in rendering, which really slowed down the rendering loop. So I removed some of those as well. But you can do a lot of interesting stuff with the interaction. So if you move something here, all the dialog boxes and everything updates in real time. And that's really something cool to see in action. I will just show you that here as well. So let's see if I can. I will go from. So this is the application, how it looks today. So you have this workshop board here you can add stuff to. You can create nodes like this. You press shift, you can move up. I added shadows here as well to be able to see when you draw a node like this, you can see a shadow here as well. What you can see the plugins here is available in the create section here. So there is the directory where you can add files to, and then you can do, for example, a DOM. You get this plugin, the dialog here, and you can just place it here, and it creates a DOM from the code. Let's see here, bridge. then you can interact. Oh, I pressed the wrong button, this one. So here you can see I can interact with this model. I can show the normals here. So if I draw the forces in the structure will update automatically. And I can also show, let's see here, a bit larger example here as well. So this is a larger example like on an airport, and you can select here and you can calculate. So the normal forces, you can also see the moment forces here. And I also did a special mode here. So these are new features that are added from, I have an X-ray mode here where you can see it adds together things in this. So you can see the forces. You can also see, if you click on the node properties here, you can see the properties of the different beams here. And if I calculate again here, this is what you get with the image mode user interface. It updates in real time the values of the forces inside the selected beam. So future development. So next step, update IVF++ to modern OpenGL, shaders for better fidelity, shader-based shadows. I have a really based simple shadow which just flattens the model, makes it gray, and draws it on the floor. So it's easy. JSON-based file format. I currently have just a very simple streams-based format now. Perhaps try porting it to WebAssembly using MScript and to see if I can provide user interface on the web. Make the computational engine plug-in based so you can run DLLs for the engines or for the different solvers. Visualization of Eigen mode, so that's a structural mechanics thing again. Also provide a 2D model, 2D view of this in the same application. Shell elements to be able to do triangles as elements as well. So that was my talk. And these are my addresses here if you want more information. I'm over time.